All right, guys. The last one is called a matched pairs design, and there's kind of two ways you can do this. If you're using two treatments, mini blocks are created in one of the following ways. Two, get rid of the word of there. That's my bad. I don't know how to type. Two very similar experimental units are separated, and each is assigned one of the two treatments. Okay, so let's say that I wanted to try something out with tennis players. I would take my two very best tennis players and give one a brand new racket and the other one the regular racket that they had. And maybe it's a new thing, it's a lot lighter, and the strings are a little tighter, and see if they can hit the ball harder. By doing this, I separate them into very similar experimental units. I separate them into little mini groups, and then I give one the treatment and one the control or whatever. That's a matched pairs design. And then here's another one. This is the one that I'm used to. This is kind of a newer thing in this edition. Each experimental unit is assigned both treatments in a random order. Now, let's say if we were trying to find a new way for you to, let's talk about standards-based grading. That's fun. Maybe I would randomly assign my AP Stats classes so that period 3 does chapter 5 with standards-based grading, and period 7 does chapter 5 with traditional grading. And then I flip them, and period 3, they get the regular traditional grading for chapter 6. And period 7, they get the standards-based grading for chapter 6. So you see what I mean? You get both treatments, and instead of comparing to somebody else, you could compare to yourself. Okay? Let's look at page 260. There's an example on an additive improving my gas mileage. Oh, cool, it's short. A consumer organization wants to know if certain fuel additives, something you would like put in your gas tank along with gas, increases the fuel efficiency in miles per gallon of cars. A total of 20 cars of different types are available for testing. Design an experiment that uses a matched pairs design to investigate this question. Explain your method of pairing. Okay, so here's what they decided to do for the matched pair. Give each car both treatments. Give each car both treatments. That's this down here, part B. Give both treatments to each car. It is reasonable to think that some of the cars are more fuel efficient than others. So using each car as its own pair by giving it a control and then also the treatment, that's a pair, accounts for the variation in fuel efficiency in the experimental units. For each car, randomly assign the order in which the treatments are assigned by flipping a coin. Heads indicates using the additive first and no additive second. Tails indicates no additive first and then the additive second. For each car, record the fuel efficiency after each treatment. Now, the reason we would flip a coin for the order of these two things is if we went with the additive first, maybe there's an after effect when we go to put the next tank of gas in without the additive, that just kind of a holdover. And so we think that we see something and we don't, or maybe in the case I just gave you, it doesn't look like there's that much of a difference, but it is because of extra additive left over in the gas. So we want different cars to be in different orders so that we can tell if that happened or not. Okay, so in that example, I'm going to draw up the diagram. Here we go. 20 cars. You take your sample and you write your sample first. Now, I'm going to go over to this. This will be a random assignment, but it's not a random assignment to two different treatments. It's a random assignment of order of two treatments. Some cars get the additive first, some cars don't. They get the additive second. So here we go, random assignment of order of treatments. All the cars are getting both treatments. Okay, group 1 will be 10 cars, and group 2 will be 10 cars. Then what happens with group 1? They get treatment 1, which is the additive. Doesn't matter if you put that in the top or the bottom, it really doesn't matter. Treatment 2 is no additive. Okay, and then I need another arrow because they have to go through the other treatment. So here we go. Whoops, that should have been treatment 1. Sorry about that. My bad. They're both treatment 1. So this one turns into treatment 2. That will be the no additive. Sloppy. And then this one will have a different treatment 2. That one will have the actual gas additive put in the car. And then what am I going to do? I think I'm going to compare. I'm going to run out of paper here. I'm going to compare what happened, and then I'll bring them together and combine and compare. So that's as best I can do that because I wrote that so big. I'm so dumb. All right, so there you go. I take my sample and I randomly assign them to the order they're going to get the treatments because I don't want the order they get them to be a lurking variable. So group 1 is going to get the additive first, no additive second. Group 2 is going to get no additive first, additive second. That way I can compare and see if they're different because of the order, and I can study that further. Then I want to compare, and when I say compare here, I mean I'm going to compare the same car that went through 2 treatments to see if it's any different. So I will have 10 different comparisons. And down here I'll have 10 different comparisons. Then I'm going to combine them and see what the truth looks like. All right, you guys have a check your understanding to do. It'll be the last thing for you to do today. Go to page 261, read your check your understanding, and fill this whole thing out. It's going to take you a few minutes, but I highly recommend that you actually go through and do this. I'll be back with the answers in a second.